There's going through some of the stuff that you missed. Here we did vector math notes, which was a little repetitive, but I don't think you were here for either of these. So we did mechanical equilibrium notes, which I think you were here for. Um, where we just kind of reviewed the second part of mechanical equilibrium. We talked about the differences between static and dynamic equilibrium, which is the idea that one thing is moving and one is not. So you can see not moving, that would be me pushing on it, but the thing is too heavy to move, so frictional force. Actually, no, you definitely questioned me on that because you said something about, well, what about increasing speed? And you're absolutely right. As the speed increases, the frictional force becomes a little bit different. It changes into a different type of energy, but it does increase because you're heating it up. So that was a great question. Vectors, we reviewed this, so I think you were here for this one. Looking back at the date. Okay, maybe not. Maybe you were here for the review. So, uh, so the challenge that a lot of people are having is the parallelogram rule. Just understanding this is a force, and this is a force, and this is a force, and the sum of the forces, the net force, is the result. The resultant is the net force. A lot of people have had a challenge with that, and that's how you determine it if you aren't given numbers. Okay, and a challenge that people have is when it's not at a right angle. So, and even I wasn't perfect at making this a perfect parallelogram. Um, I'm sure you know, but I've been telling them it should be train tracks. Like this line and this line should never cross. What a lot of people are doing when they get this, actually, here, let me get an example problem that people are struggling with. Here we go. When they get to something like this, they're just doing this and this, and that's wrong. You need to be attentive to the parallelogram idea. So I'm not great because I don't have a good straight edge with me. That still is a very parallel. Notice I am trying to make a parallel line with that. And then this parallel line. And then the resultant, the net force, is here. When it comes down to these, you have your resultant and you're trying to figure out the forces that cause this to happen. So I kind of make up my dotted line, show that resultant occurred with a force that long, and a force this long. Okay. This part has been a bit of a challenge because a lot of people draw the parallelogram but not the actual force vectors. So when you do the function of that, that's how you do that. These I'm not really stressing about. It's the same as these, but unnecessarily complicated. Okay. Here's the part where you missed, I'm pretty sure. This is the part that gets a little confusing. I'll do vector math notes first. Uh, okay, so here are the notes that we did, and I'll leave it up for a minute for you to kind of peruse and explore. Well, what I want you to understand is, okay, we reviewed scalar and vector. We reviewed the parallelogram rule, all right? Um, and this was me trying to diagram a barge, think, or a boat being pulled down a river by ropes on either side, which is not something that happens now. It's a dated factor, but the result is it will go straight. And the reason why you draw a parallelogram is to help find your result, or your net force. Okay, this is where people get confused. And what I'm going to do, I'll just go ahead and add a page and work that out. The confusing component of this is that um, we've been working with Nellie Like, here she is. She's hanging on this trapeze bar, right? And her weight is evenly distributed through each of these lines. Great, wonderful. The problem comes when, what if she's on a zip line? Like, what if it's a terrible zip line? I'm going to do my terrible zip line example. Here's Nellie, zip lining with her gear, like she has a helmet on. Okay, here's Nellie zip lining through the rainforest. When you suddenly create an angle, like these each have a nice 90 degrees, they're directly oppositional to gravity. When you have a steep angle such as this, the weight of Nellie, I'm going to go 2.5 squares down. Theoretically, like if there was just one rope and she was Tarzan swinging through the jungle, she would have this upward tension. But in this case, she does not. The tension is distributed to these two components, to this rope and this side of the rope. And what I had the boys do, and you can try this sitting down, if you had hip surgery, if you have any sort of weighted objects, hold them up in the air, straight up ahead like this, right? Okay, you hold your object up. You could be there all day. I gave them 3-pound weights. But what if you change it like this? What if you pull your arms out to a T shape? How does that affect your ability to hold that weight? What's happening is the tension is increasing by a significant amount because you're now adding a different component, a different part of the vector. Not only are you dealing with the downward force of gravity, you have to consider that there's a horizontal force as well, and this is now your like resulting tension. So mathematically, you would need to use trigonometry, so sine, cosine, to solve this, and that's not something you usually do or take until after, well, geometry and up. So we're going to refrain since conceptual physics. But I just want you, one, to understand Nellie's hanging on these ropes, her weight would be split evenly. So if she has, here, I'm going to draw this more accurately. If she has a 2 square weight, this one is holding 1 square weight, this one is holding 1 square weight. My blue arrows are now inaccurate. In this case, if she's 2 squares of weight, how you're going to have to solve this is use your imaginary tension line and draw your parallelogram now. Forgive me again. Wow, that's close. There you go. This one is parallel to this one. And then draw your parallel line again here. Okay. Now, this is the tension put on this rope. If you were to turn and measure it, it's about equal to Nellie's weight. So rather than splitting her weight evenly, like this example, it is now taking, because it's at such a severe angle, this is approximately Nellie's whole weight. So if she's 60 newtons, this side rope is taking on 60 newtons. This side rope is taking on 60 newtons of force, approximately. Mathematically, that's probably inaccurate. But if you visualize the boxes, we're close. We're close. Maybe it's greater than 60, right? Maybe it's 60 plus. The wider your angle, the increase in the forces. And this is how you determine the forces, the length of the force. And this is why we also have graph paper to make sure you're consistent in your drawings. So if you say Nellie's weight is 2 squares long, or 2 and 1/4 squares long, you have to replicate that same as your imaginary tension line upwards to get an accurate force reading. Okay, so if I scroll down and I put Nellie on an even tighter line, and I'm having, again, no straight edge. There's Nellie. Nellie's getting messy because I don't want to belabor this. Okay, 1, 2, a little bit more than 2. Now imagine what's going to happen here. A little bit more than 2. If I try and draw this parallel line, it's going to be that. And that's not even very good. It would be even steeper than that. It would be like this. And it would be like this. Okay. Notice our force. So sorry about this. Notice where that crosses. And this is me just eyeballing, not using a straight edge. All of a sudden, her force like quadruples on the line. Right? That's exactly what's happening when you hold those weights out at the shape. Okay? Your arms are held out like this. When you hold out like this, you're taking that weight and it's essentially acting as if it's doubled the weight or the or the force. So that's the biggest thing that you need to understand with Nelly. We're not going to calculate it. There will be no numbers. Your magnitude will be represented in arrow sizes rather than anything else. And that's what we're going with here. Like here, you did your reverse tension. So this, this, this clearly demonstrates A is taking greater tension. It's greater than B. Right? Same thing here. We would draw this. This is just me eyeballing. B this time is greater. So again, test this out in your packet. I think that's the hardest concept. Some other things we did review is just remembering and adding and dealing with the sum or the net force of vectors. You have something far north, south, and east. If this is 50, this is 10, you would need to shorten this to make it 40 versus 60 newtons. This is when you use Pythag. But I'm pretty sure I hit that pretty hard with your class. Let's see, mechanical equilibrium. Check me on that. I'm going to stop this video here because I only get 15 minutes of time. But check me on that. If I didn't go over Pythag with you guys, I'm not seeing it in my notes, but I was also having technical difficulties with some of it. So let me know if you need me to go further into depth with Pythagorean theorem. Okay? All right. That's all I got.